All right, class, welcome back. This is the Chapter 8 lecture on thin-walled pressure vessels and combined loadings. I'm going to be doing overviews of all of the lecture slides that are going to be posted on Google Drive, as well as the worksheets, so keep an eye out for those. Anyway, my name is Derek Banerjee, in case you're not in my class. Check the eCampus schedule for my Zoom office hours, and there's my email address. Now, Chapter 8, again, combined loadings with a little bit of pressure vessels. So up until now, we've talked about these four main types of stresses caused by these four main types of loadings here. All right, we got our internal axial force, our shear force, bending moment, torsional moment, causing our average normal stress over a cross section due to that axial force. The shear force, that's chapter 7, our transverse shear, causing our shear stress VQ over IT. And then chapter 6 was our bending moment with our flexure formula, where our normal stress is My over I. And then chapter 5 was our torsional moment, causing this torsional shear stress, right? T rho over J, our torsion formula. Right, so we spent a lot of time talking about all of the different stress distributions that come from those internal resultants and calculating a lot of different cross sections, and there's a lot of variations of those. Basically, what we're going to start doing now is combining them, as is implied by the name combined loadings. Right, so the problems are going to get pretty complex, but the way to treat them is basically just to break them into their parts. And then we're going to use the method of superposition to add up those parts to get our resultant stress distributions. Now, before we get into combined loadings again, though, we're going to talk about one last type of stress that we're going to see, and that is normal stress that's going to build up in pressure vessels. First, though, what is a pressure vessel? Basically, they're just closed structures that are holding liquids or gases under some pressure. You probably have a lot of them lying around your house, beverage containers for sure, tanks, pipes, pressurized cabins and aircrafts and space vehicles, other examples. But in this class in general, we're going to consider just thin-walled pressure vessels, as most of them are, and of two main shapes, that's cylindrical and spherical. And provided that our vessel walls are thin, we'll talk about what that means here in a second, but provided that it's thin, we are going to assume a uniform stress distribution, and we can get the stresses in a pretty straightforward manner. We'll look at actual elements of the material on the vessel, right? So thin-walled, going back to that, basically just means this ratio of radius over thickness. Here our inner radius is our distance from our center to our inner wall, divided by the thickness of the wall. If that value is greater than or equal to 10, then we can consider it thin-walled. So we'll check for that when we're doing our problems. All right, now how do we actually find these stresses? So first, in the case of both spherical and cylindrical pressure vessels, we're always going to talk about a gauge pressure. So that's the pressure above the atmospheric pressure, basically because we assume that the pressure vessels had atmospheric pressure before they were filled with whatever liquid or gas they're filled with, right? And the other kind of dimensions that we're going to look at, again, thickness, T, and the inner radius, R, and then we have that gauge pressure that's built up within the vessel by a gas or liquid. And if we look at a cylinder here, we look at an element on the side, what ends up happening is we have what we'll call biaxial stress. We have two normal stresses, one in each direction. Okay, this is the Y direction, and then one in the Z direction. And those are what we're going to call sigma 1 and sigma 2. I blew it up here so you can look at it more closely. In order to find what those are, basically what we do is take a cut through what we're going to call the circumferential or hoop direction. And if we find a resultant force due to the stress on the wall here, so that'd be sigma 1 times 2t times dy, Okay, this area here is T times dy, and there are two of them. That has to counteract the pressure that's acting over area of 2r times dy. Okay, if you solve for sigma 1 there, you conveniently get this nice equation here. So our normal stress is just going to be the gauge pressure times the inner radius divided by the thickness. All right, and then for the longitudinal or axial direction, we're going to cut through the cylinder like this, and sigma 2 is going to be acting on the circumference of your cross section, so that's going to be 2 pi r for the circumference, and times the thickness T is the area that it's acting over. That has to counteract the same gauge pressure times this inner area, so pi r squared. Solve for sigma 2, you get sigma 2 is equal to PR over 2T. If you want to see those equations, check it out in the textbook for the equations of equilibrium. But the key things to take away are these equations here. All right, so again, circumferential or hoop direction, that's going around the circumference, is this up and down direction here. That's PR over T. And going in the longitudinal or axial direction is PR over 2T. Notice that that is half that of the circumferential direction, which leads us to how these vessels tend to fail. For a cylindrical pressure vessel, again, in that hoop direction, it's a higher stress, PR over T, so it's going to tend to fail in that direction. So what happened to these tanks here is they started to bulge out and then ruptured because of the hoop stress. All right, now looking at our other type of pressure vessel, the spherical pressure vessels are analyzed in the same way, but due to their symmetry, we just have this hemispherical shape when we cut into it, and what we end up getting is the same thing as our longitudinal or axial stress for this resultant here, and due to the symmetry again, we're going to have that same stress on the other side. No matter how you orient your axes, no matter how you orient your element, you're going to end up with sigma 2 and sigma 2. All right, again, I mentioned that we have biaxial stress, meaning we have normal stress in two directions, as opposed to, up until now, we were always talking about uniaxial stress. Just one normal force gives one normal stress. All right, we're going to look at these elements a lot more in the rest of this chapter, and especially in chapter 9 when we do stress transformation. So get used to starting to look at the stress on elements, 2D and 3D. And that's it for the first section of chapter 8. You can go ahead and try the first worksheet problem, and then I'll see you in the last bit of the chapter 8 lecture slides.